So today we're going to take the information we learned in the nuclear and then also the stuff we learned in the combustion sources. So that was over a week ago, but we talked about all the different combustion sources of energy. And we're going to be looking at electrical sources and then how to store electricity. Because so far, I mean, when we think of portable electricity, the most portable really is just carry the chemical fuel around. That's why we use gasoline and diesel for our transportation needs because it's incredibly portable. You only need to carry around the fuel. The oxidant is freely available in the atmosphere. So you only really need to carry around half of the reactants. But we're moving more towards electricity. We'll see some examples of why. But it's not that portable. You need a way to store it. And so that's a real problem technology wise. And so the sources, of course, for electrical energy are oxidation and reduction reactions, okay, and electromagnetism and physics. We don't really use that very much, but we do see that. We're using that in terms of our cordless chargers. So there's an oscillator in there, and there's a pickup coil, and so we're just using radiation to charge our phones, but it's not ionizing radiation; it's in the radio frequency. So we just set a coil on there and use electromagnetism to charge up our batteries. And photovoltaics, we'll see how those work today too. And then there's different storage things. So today's really kind of a survey of just going through a lot of the different storage technologies that we have, because that's one of the issues with electricity is because a lot of the storage is lossy and has a high impedance. So impedance, think of the word impedance. So an impediment is a hindrance, and so if you have something that is hard to think about electricity, hard to charge up, it's impeding the charging. Like there's only so many amps you can stuff into a battery. You're stuffing joules in there by running this electrochemical reaction backwards, but how fast can that reaction go? So the chemist calls it kinetics, but electrical engineers call it impedance. How fast you can put electricity in and how fast you can get it out. That would be the impedance of the source. And then once you get it charged up, does it lose its energy? You put in 100 joules, can you get 100 out? You go and try to pull it out, and you get 75. So now you've got a 75% efficiency. So we'll look at a bunch of different flow batteries and systems today and we'll sort of classify them based on their charge and discharge efficiency. So put in 100 in, get 75 out. That's better than putting 100 in and getting 49 out. So that's what we're going to look at. So this is the governing chart that we're going to be thinking about in terms of all of these different sources. We've already talked about combustion, which would be chemical fuel going to thermal, going to mechanical, going to electrical. So if we want electricity, and we're starting with coal or natural gas, then we got to boil water, turn it into superheated steam. That's our thermal energy. We need to use that superheated steam or other kind of gas to spin a turbine. And then now that we have the spinning turbine, we clutch that into an electrical generator and we get our electricity. We could go straight to that if we had a fuel cell, and we're going to look at some of those. So if we have chemical reactants that react with each other, produce electricity, maybe we could make a galvanic cell and make that electricity go through our system and produce an electrical potential. Now we have electricity. And the flow cells we'll see today can be run backwards through electrolysis. So we can charge it up, and there's efficiencies associated with that. So using electricity to charge up a fuel cell, we'll use these numbers. These are the maximum values I could find. So we're stuffing electricity into the flow cell, so we're making chemical energy, and then we're discharging it back out with the fuel cell. And then solar energy is commercially available. It's pretty easy to get 15% efficient, but they're pushing the 20s. And so I don't know how efficient our modern solar cells are, but that number has got a lot of potential for growth. You look at all of these, 88, 46, 98. I mean, there's not much potential for growth in electrical generators. But when you look at solar cells, 15%. That's why a lot of people are doing research, like Dr. Trad, on photosensitized photovoltaics. Also, look at how much how much we throw away in terms of light. So we run electricity through a hot filament and heat it up. We get light out, but only 4%. If that's what we want, like how do you classify your efficiency? It's like how much of what you want comes out of the process. And so if we want light and we're heating up a wire to make light, only 4% of the energy comes out in the visible region. A whole lot comes out in the infrared region, but we want the visible light, and so the incandescent bulb is a real energy waster if you're focused on the performance of the bulb. In terms of our household usage, it's not very much. It's maybe 10% of our household energy bill. So 10% is not zero, but 90% is heating, air conditioning, cooking, water heating, all of the heating stuff is the 90% of our household bill. So you can turn the lights off if you want. That's good. I mean, saving 10% is good, but you're not going to cut your bill in half by living in the dark if you want to stay at a comfortable temperature and you want to cook food. So this is the energy flow diagrams that we see. Lawrence Livermore produces these. I absolutely love them. So this is from 2002, so quite a while ago. Net primary use was 115 exajoules per year, so that was a huge amount of energy. Remember, an exajoule is 10 to the 18, so that's an incomprehensible amount of energy. And these are the primary sources over here. So coal and natural gas and biomass and hydroelectric and nuclear go into our electrical power plants, and maybe a little bit of petroleum, not much, goes in, and out comes 12.5 exajoules with 40% or 40 exajoules going in. So that's a 31% efficiency for our electrical grid. So that's pretty pathetic, but that's what we've got. We put in 100 joules and we get 31 out. So we're really getting hurt in terms of what we get out of our electrical system. And this is distributed energy. So this is actually what was billed. You say, well, that's not fair. What about what was produced? But if we produce more than that and only 12.5 exajoules got billed, that's really all that was used. The rest was lost. So it doesn't matter what you produce. It matters what got actually to the residents and got used in the air conditioner or in the heater. So this was what was billed, was 12.5, the distributed energy. We could look at residential. So this energy comes in the form of electricity, natural gas, petroleum, and when we bring in 20.7 exajoules and we use 15, we're at 75% efficient. So that's good. Now this 8.9, okay, is coming in here, but it came from electricity that was at 31. And so it's actually worse than 75% because we're sitting on top of a 31% efficient spot here. So in those places where natural gas and coal and petroleum, very few houses use coal, but there's a number there, 0.1. Okay, these are direct uses of energy, and they are going to be more efficient than using electricity. So if you've got a stove and you want to heat something up, burning natural gas is way more efficient than using electricity because you've already lost 70% of the joules making the electricity. And so if you just want to heat something up, the thermal heat from chemical to thermal is 88% efficient. And if you're using electricity, you've already cut it down to 31% efficient. So industrial is even better than household, and that's because they do better at managing their waste heat. So they'll use waste heat from their industrial process in their facilities. And the transportation is coming in at 20%. Okay. This is a long time ago, 2002. How are we doing in a more recent time? So here's 2019. Still pretty good. The electrical efficiency got better, 34%. Residential fell a little bit because we cut back on some of the petroleum use. see, 5 exajoules of natural gas. We cut back on that. 8.7, we dropped to 5, and then we saw an efficiency drop. Okay. So now when you look at if you go to Home Depot and you want to buy a hot water heater, they're going to this is a 91% efficient appliance. And that's true that 91% of the electricity that comes in produces 100 joules in, 91 joules of heat in that water. But notice that doesn't take into account the efficiency of the power plant. Okay, so we're missing that efficiency. So now what about 2020? This was the COVID year. We saw a drop in use. We're still around 100 exajoules. A quad and an exajoule are only 5% different. So about 100 exajoules of consumption in 2019. Then COVID hit and we dropped 92 to 93 exajoules. So that's only 7 exajoules. But think of the disruption we had during the COVID year, 2020. It was pretty huge. And yet it didn't cut our consumption of energy very much at all. So, yeah. Homes are still at 65%. Transportation was still same at 21%. Industry, let's see. Industry, I don't see, this is 80% in 2002, and it looks like it dropped to 50%. So that seems unusual. I don't know what happened there. 49% in 2020, and then I went this morning and got the 2023 number. So this is again from the Lawrence Livermore flow charts. The address is down here at the bottom. Residential still at 65. Notice we've come back up a little bit from COVID, but not much. We're at 93.6 exajoules. And the overall United States got a little bit more efficient at 34%. So. Now you may look at this and say, well, what about this big transportation number? You know, that's using all of that diesel and gasoline. And wouldn't it be better if we ran it on electricity with this big push of electric cars? Notice by the time you get to here, electricity, you're at 42%. And then we're going to run this down here. Now, the electric motors are more efficient than gasoline motors. Okay, so you'll see an efficiency gain by using electric motors versus gasoline motors, but you're already sitting on 42%. And so this process would have to be greater than 50%, because we've got to beat this number. And if you're already at 42% and you multiply that by 0.5, then you're at 21%. And so that's the number to beat for electrical vehicles. Now, maybe they beat that. I don't know. I don't have the numbers on electrical vehicles, but that's the number to beat. It's not going to reduce our carbon footprint much because of this right here. These carbon sources for our electrical generation are a real problem. So the thing I'm looking at and saying, well, we're building out the infrastructure for charging cars, and that's expensive and it's huge. But we're not building out our infrastructure for the carbon-free electrical systems. We're trying windmills and some solar, but really nuclear is the way to go, I think, in terms of capacity. So nuclear, this is the carbon dioxide emissions from different sectors. You can see transportation has the largest footprint right here. But electrical generation is comparable. And unless we incorporate more of these sources into our electrical grid, then we're just shifting carbon from one source to another. We're just going to be moving it over here to electrical. Now, there's different kinds of power plants too. So there's the difference between base generation here, which we can run at its peak efficiency, coal, nuclear, hydroelectric. And we want those to run at their optimum speed. Now, you might have noticed if your car has a tachometer, like the RPMs needle, there's like a sweet spot, right? When you're accelerating, you can really feel the pull of the car. It's at its sweet spot. And that's in your RPMs. That's its most efficient RPM for that engine. If you go too fast, it drops off. And same with any kind of motor. And a power plant is a motor. And so we want to run our coal or nuclear or hydroelectric plants at their optimum RPM, if you want to think of it that way. And that may or may not meet demand. It's best if it doesn't, because then we can use these other power plants, like a gas turbine power plant, that can turn on and turn off very quickly. So this is one that's very adjustable. And so that's what we're using for load leveling. So we can turn off our natural gas pipelines over to midnight to 6 a.m. time frame when we don't have a lot of demand. And then when people wake up, they start turning on the heaters, or if it's summertime, they turn on the air conditioning and so on, start getting ready, then the electrical demand jumps up. All the office buildings, the lights come on and the air conditioner kicks in and so on, and the demand just rockets up in the morning. And so then we can turn on those natural gas turbines. But what if we are at maximum capacity for those natural gas turbines? What are we going to do for this region here? It would be nice if we could, this is the cheapest fuel here. Natural gas is pretty cheap. But if we run this up here to this level, then we can be able to charge or store that excess electricity. So we're not using it, we're storing it. So we're putting it in the bank, and then when demand goes up, we put it back into the system. And so that's a lot of the stuff we're going to talk about this morning too, is load leveling. So let's look at our homes. A typical home runs on about 1,000 kilowatt hours a month. Okay, and we can just look to see how many amps that is. The power is volts times amps, and so we could look at if our homes are running on 120 volt systems. And there are a couple of 240 volt things like your clothes dryer and your oven, but let's just, for sake of calculation, let's say the whole house is 120 volts. This many watts are coming in, so that on average that's about 11.8 amps. That's just not that much if you think about it. Now I've always wanted to do this, I never have, but turn off all my fridge, unplug everything in the house, and just see look at the meter with the lights and everything on, and then turn off all the lights, and then look at my meter and see how much energy it's consuming per hour and so on. And you can use your meter if you're really curious about all of this, and you can see how much current is being drawn by parts of your house. You can also use those meters that we have in the PChem lab, the loop meter and the clamp. So you can plug your fridge in to the wall with one of those loops and use a clamp style ammeter, and you can get the amps, and then you can measure the voltage, and you can get the power consumption of your fridge, your washer, your dryer, and so on. And so let's look at the different energy storage mediums. So here we are looking at like large scale versus small scale. So large scale energy storage, this is one that's really good. It's using the gravity or compressed gas, and this in particular was showing gravity. So you've got a hydroelectric dam, and when usage is high, you're running it at peak efficiency and you're supplying energy to the grid. People are using that, and then midnight comes along, people go to sleep, they turn off the AC or the heater, and demand drops. They're not cooking their food, etc., not heating their water. And they keep this power plant running at peak efficiency, and instead of using it to generate electricity, they use electricity to pump water uphill. And so they'll have this reservoir up on a hill that they're pumping water up to, and they're storing excess capacity. It's really just like a capacitor. Most of our capacitors are electrical charge. We're separating positives and negatives and storing that energy, and then we can use it later to run an engine or whatever. But this is storing water uphill, so we're using gravity. We just pump water uphill, and it's sitting there ready for us to use. Then around 6 a.m., demand goes up, the grid needs more power, they start pulling that water off the hill and generating electricity. Now that's large scale. That's what we call commodity scale electrical storage. There's also like rapid, uninterruptible power supplies, rapid response, and this would be a couple of examples of that. These are flywheel storages. So when you want to store the energy, you start spinning this this weight. It's like a cylinder, a weighted cylinder, and you have a motor that can be flipped into a generator. So when you want to store the electricity, you spin up this object really heavy inside this vacuum chamber, and so it's stored that energy in mechanical energy, so mechanical energy storage. And then if you need it, let's say there's a power outage and you've got your computer system sitting there, it needs good power, then you clutch in and start generating it from that flywheel. And so these things can store kilowatts of energy. So this is the storage spectrum. Down here, UPS, uninterruptible power supply for small devices. They can store energy for, minutes and seconds. Okay, and they can store, 10,000, 10,000 watts to 100,000 watts. And then up here, what I was talking about, commodity storage. This can, store it for days on days, and it can be up to like 100 megawatts. So this would be like pumped hydro. So that's something to keep in mind in terms of our grid stability, both of local. So this would be, you can think of this as local. You would have this at your house, and this would be like a central site, like a power plant. So not really local. So let's go through some of these interesting flow cells. So most of our batteries you have to change out, and that's annoying, isn't it? That drives me crazy with the like some of these rechargeable doorbells and stuff like that. All of a sudden your battery's out and you got to go charge it up, and that's inconvenient. And the smoke detectors drive me crazy. We went and tried to sleep at my mom's house, and all the batteries were like 3 smoke detectors going off, and it beeps every 20 seconds or something. So you're running around the house saying, "Is it in this room?" Beep. No, if it's in the other rooms. Then you run over there and you hear finally another beep. And anyway, we finally found them. She had 6 smoke detectors, and 5 of the batteries were out. So we just replaced all of them. It's driving me crazy. A flow cell, though, does not have to be swapped out. So this is a battery. It's an electrochemical cell, but it has a constant flow of the reactants. So you have some regenerative fuel cell, and you always, this is the current limiting step here. You always have a cation membrane. Or some sort of porous barrier that the cations flow through, and the electrons go this direction. So the electrons are going this way, back and forth, depending on whether you're charging or discharging, and the cations go back and forth whether you're charging or discharging. And so they keep most of the, these reactions. You've got your 2 half reactions, and they have them completely separated. And so the cations go through the ion selective membrane, and the electrons go through your circuit. And then when you're charging it up, you pump electrons in, and that forces the cations to go the other direction. And then you have these storage tanks. The nice thing about this is you can analyze the reactants independently. You don't have to turn the circuit off. You can say, "Hey, are my reactants still pure? Are there impurities in there? Is something wrong that's going to hinder the reaction or foul my membrane?" and so on. And you can do what we call surveillance. So you can surveil the reactants, make sure that they're still good, add more if there's some kind of reason why they might be precipitating out or some kind of problem, and you can maintain flow cells. So flow cells are great. And so this is again, we're talking about huge 15 megawatt concept flow cell using bromide and sodium and sulfur. Here's another one, a vanadium cell. So vanadium's a crazy metal. Look at those oxidation states. 3 and 2 and 4 and 5. And so this is using half reactions that are vanadium on both sides, which is pretty cool. And you got a 2 to 3 transition, and you got a 4 to 5 transition, and they happen at different voltages, and so you got a potential difference, and so you can run a cell based on vanadium. And this is really good because look at its efficiency. So the charge discharge rate is about 85%. So this is, again, some of these things were invented quite a while ago. This is from the 1980s. Okay, it's been applied at 20 commercial sites and has up to 8,000 megawatt hours of installed usage. Here's one in a 53-foot trailer, so that it fit on the back of a 18-wheeler. And this is the zinc bromide fuel cell, and so it's using zinc and bromide, and it's got the cation membrane. So in this case, zinc would be crossing that membrane back and forth, and it's about 75% efficient. And this has been deployable as local power stations. Then there's the tried and true lead acid battery. We know lead acid batteries work. They're not really technically difficult to make, and so they charge and discharge pretty well. And so here's one in California, a 10 megawatt battery storage place. And here's a worker. You can kind of see with the person here the scale of the facility. There's a lot of sulfuric acid in that building. And these are the lead acid batteries. They're a lot bigger than your automobile batteries because they're made for power applications. So this one I call the fire and brimstone battery because it's got liquid sodium, molten liquid sodium, okay, and sulfur. And the cation, the sodium channels can go through this porous plug, this beta alumina tube. And so again, your sodium transfer through that membrane is going to be your current limiting step, and it gives you a 2-volt difference in your electrical potential. And so you just stack these up in series, and you can get up to whatever voltage you need. And this one is in Japan. It's a 51 megawatt wind farm. And so that's the problem. When you have windmills, the power is intermittent. It's generating when the wind blows. What are you going to do when it's not blowing? You need some sort of battery storage that's getting close to commodity scale. If you're trying to hook this wind farm up to the grid, you want to be able to stuff substantial amounts of electricity onto the grid, and you want to be able to not throw it away when demand is low. Let's say at midnight to 6, we got a really low demand. The grid is topped off with coal and natural gas, and the wind's blowing like crazy. You're just throwing that electricity away. And so we need to have battery storage to make wind energy useful. And this one is about 89% efficient. So far, this is the best one in terms of the flow cell. I would hate for that to get a leak though. Water, sodium is oxygen and water reactive. When it gets in wet, it will strip the oxygen away from the hydrogen and produce hydrogen gas. And if there's a spark, then the hydrogen gas will catch fire. And sulfur is flammable, and it produces poison gas. Sulfur oxides are poison. So if this thing were to catch fire, it would be impossible to put out, and it would produce toxic sulfur oxide gas, and it would be a terrible thing. Lithium ion batteries, the lithium is great. I mean, as far as the conductive barrier, so lithium ions can be conducted very quickly through these membranes, and so these are good for high current, and they have a really high efficiency. It's approaching 100%, and so that's why these different lithium batteries, there's lithium ion batteries, there's lithium polymer batteries, there's lithium phosphate batteries. There's a lot of batteries that are based upon using the conductivity of the lithium ion through the barrier that can be done at high current and repeatably. And so that's why it's the leader. There's even metal air batteries. All of your little button cells, they're using oxygen as one of the reactants. And so there's a little porous membrane around there where oxygen can diffuse into the battery. Not very good for power, meaning high wattage, because the oxygen's not going to flow into that battery very fast. It's going to diffuse into the battery. And if you want high current, capacitors are the way to go. So just separate the charge, so charge it up, and then it can discharge incredibly fast. So for acceleration, and I'm pretty sure that the automobiles use ultracapacitors. So they have batteries and then they have ultracapacitors for the acceleration step. And it will also charge up quickly. So when you hit the brakes, where is it dumping that electricity? The battery can charge pretty fast, but the capacitors can charge even faster. So it's a great way to top off those capacitors, and then when you accelerate, then it can dump that charge back into the motors and give you a high current, so that the battery isn't experiencing these high current shocks or high current drains. So you can put capacitors in between your batteries and your motors and handle the high current events. And then this one I'm pretty excited about. The pumped hydro was good because you're pumping the water uphill. You can use the same hydro plant to generate electricity. This one seems a little crazy. Um, so they run the power plant. This could be a natural gas power plant with the steam, I mean a gas turbine. There's nothing new about that. But then at off-peak hours, instead of turning it off, they just pump air down into this limestone canyon. And so they just run the pressure of this canyon up. And so that's another way to store energy, right? Pressure. You're compressing a gas. The heat from the compression too is just put right into the ground. There's not a problem there. So they could stuff that gas into a canyon. And then when the demand goes up again, your gas turbine is still running at its peak efficiency. But then now we can supplement it with another turbine pulling the air out of that canyon and spinning a separate turbine for the high demand. So we can run that natural gas at peak performance and either pump air down here or generate electricity with the air. So it's pretty good. And then here's a picture of the pumped hydro. Again, at 70 to 85% range of efficiency. So about 3% of the global generation capacity is, and we're talking about now gigawatts, not megawatts, 90 gigawatts of pump storage. And a lot of these, it doesn't look like this one does, but a lot of these will have polypropylene balls like covering the whole surface to prevent evaporation and solar heating. And so I've seen black ones, but I'm sure they use white ones too, to reflect the sunlight. And so it'll keep the reservoir cool, because evaporation is your enemy in this situation. You don't want you've pumped that water uphill and you don't want it to be lost. And then here's a cutaway of that kinetic storage, the flywheel. So there's no friction either, because these are magnetic bearings. And so the shaft is held in a magnetic field. And so it's a friction-free environment except for the motor. The motor has to spin it up, and then when it's discharging, the motor turns into a generator. So it's pushing that momentum through the motor and spinning the generator. It's about a 90% efficient thing. So you can spin it up. So turning electrical into mechanical is in our efficiency chart. I can't remember what it is. It's either 90 or 98. Oh, it's right in front of me. Yeah. So yeah, electrical to mechanical is 90, and then turning that back into electrical is about 98. So here's a summary of everything we talked about. So the pumped hydroelectric or compressed air storage, these are what we call energy applications. So those are for like grid level, grid maintenance. Meaning you want to keep the grid fully charged so that nobody experiences any brownouts, that the load leveling is taken into account. And then down here, the capacitors and all of these things, all the way up to like lithium ion storage and batteries, these are local. Say fine tuning. And we're finding, the batteries and flow batteries, these play that important role of in between. You know, is it a local thing? Is it storing electricity from solar panels or storing electricity from wind and solar? So so here's solar steam. We talk about electrophotovoltaics, but this is another way to do it. Just use the heat from the sun. So here's a steam installation where these parabolic reflectors are shining on quartz tubes filled with water and flashing them to steam and heating them up. And then that steam is sent over to spin a turbine. Okay. What do you think? Let's ask you some questions. What do you think would be the problem with a facility like this using solar steam? Doesn't work at night. That's good. Yeah. So you would need some sort of battery storage to hold on if this was a really hot day and you didn't need it. So then you're going to store it and then you use it at night, you know. So what are some other problems here? Too much heat could be. What is this running on really? I mean, the sun's providing the energy, but what is it really running on? Yeah. And water's a big problem. Water's a bad actor in a sense because it's hard to keep it pure. Okay. And whenever you flash something to steam, the anything that's not in that anything that's not water precipitates out. And so that's called scale. So in order to get this water to reliably evaporate, that water is going to be depositing all of its soluble metals. Calcium is a big actor because calcium oxide precipitates out in all boilers and gets on the heating elements. Okay, and we see it as water spots. When you wash dishes and let them air dry or whatever, if you've got hard water, you'll see water spots, and that multiply that by 1,000,000,000. That's what you're going to have inside these tubes, and so that's a real problem. Water's the Achilles heel for a lot of these things. Even all of our steam boilers too. Boiler maintenance is huge, and so that's our. And so these typically they want the water to heat up and superheat in these things, so the pipes in these things are going to be a problem. And that's it seems strange because the technology of just boiling water doesn't sound too difficult. When you're boiling water in a big tank and you got the heating elements there, you can swap those heating elements easily. Replacing all the pipes and the tubes in something like this would be way more expensive and way more problematic. Okay. There's also the footprint. Look at the size of this place. This is the width of a road here. Let's see. So the width of this road here is about, I've sort of put it to scale as the width of this road right here. You know, so in terms of perspective, or maybe this road right here, these are roughly the same magnification. Does that make sense? And this is because I'm familiar with it, the Fayette Power Project in LaGrange. That's where my wife's from. This is the footprint for these 3 power plants. And this one here has got 354 megawatts of capacity. Okay. But these have, you know, more than that in just one of these power plants, one of these coal-fired. So these are 3 coal-fired power plants. In terms of the footprint, this is much smaller. Now, this is the footprint of the power plant to generate an enormous amount of electricity. This power plant would fit right here. All 3 of these coal-fired power plants would fit right there in terms of land use. Now, that's not exactly fair because you've got this lake here. So this is a man-made lake as the secondary cooling for this power plant. But the lake is useful for recreation. I mean, it's a great fishing lake and you know, recreational lake. So there's some secondary use there. And it's not exactly fair either because of the coal-fired power plant requires coal, and we have to ship that in. So where do we get the coal? So this is, let me go here. This is, again, another solar park, and comparing it to the Fayette Power Plant. This coal-fired power plant is equal to 41 of these solar installations. Okay, but this is what the coal mining footprint looks like. Um, and this is how they're mining. So this is in Wyoming. So even though a coal-fired power plant takes up less real estate to make the electricity, you got to get the coal from somewhere. And so this is the footprint of the coal mines. Pretty impressive, isn't it? So this is all ammonium nitrate fuel oil. In general, that's the mining explosive. And primer cord. I love this one. Did you see all the little sparks? So they drill these holes. They fill them with ammonium nitrate fuel oil. Then they have this, it looks like Ethernet cord. It's a plastic coated cord that has explosive in it. And then they can even like join it and make little circuits with this stuff. And then they drop detonators down into the ammonium nitrate fuel oil. The ammonium nitrate fuel oil is like a slurry, and they fill those holes with it, and it's the perfect force to just break and crack the rock. And this is probably the best one because there's not a lot of powdered coal shooting up in the air. Sometimes that can catch fire when they do the detonation. This just breaks the rock up to where it's available to be picked up by dump trucks and backhoes. See, it just lays it down, and now you come in with the drag buckets and the backhoes. That's a big one. Now you may say, well, that's a bigger footprint, and it is, okay, but we're not generating the electricity in Wyoming and sending the electricity to Fayette County. We're bringing the coal here. So we were talking about what's portable in terms of the fuel is very portable. We put it on trains and bring it all the way in. And the footprint in Wyoming is, I know that they might be controversial to people who live in Wyoming, it's a lot cheaper, right? To this footprint, transmission of electricity through the power lines is very lossy. And so if we're going to lose this electricity, we need to have the power plant close to the residential areas where the property values are much higher. So it costs a lot to take up this much footprint near the city of Houston or LaGrange or whatever. And so right now, that's why we've ended up with, we've got coal mines in the remote areas, and we transport the fuel to the urban areas where we generate the electricity fairly close to where it's being used. So but yeah, so we've sort of tried to optimize things. Now you can calculate what it would take to run your house on electricity. This is a good place to go, this National Renewable Energy Laboratory. And so I did this a few years ago, and it was $8 a watt, and it was, you could get 10 watts out of a square foot solar cell. Things have improved, but let's look at these numbers. If you had a 3,000 watt home, it would cost you $24,000 to put your home on electricity, solar cells, okay? And you still haven't solved the nighttime problem. You want to stay cool at night, you got to run the AC, but you're not going to be able to do that in the dark. So this doesn't include the whole house battery that you have to buy from Tesla or someplace like that. But anyway, this is what it would take to install those solar cells. Now prices have really come down. So this is now the per watt cost. It was $8, now it's down to around $1.50. So that's fantastic. And that $24,000 for a 3,000 watt home is now under $5,000. So this is, we're really seeing, and now that's why you're seeing, if you drive through residential neighborhoods, many more people have solar panels on their houses. Now this is, this 191 foot area, that's gonna be, facing south at an optimal angle. Most people's houses are not constructed with the flat part of the roof facing directly south. They're at some other angle. And so you're going to cost more if your panels are less efficient. Okay. But yeah, this is the drop in residential photovoltaics from 2010 to 2018. So you can see it's really dropping. It's less than half of what it used to be. And then this last one we talked about in my office, the thermocouple. It's so sad. It's a dismal 7%. But we've made what we call forever batteries. That's what we put on our satellites. And so these satellites have been sent out of the solar system. What powers a satellite when it gets that far from the sun? You can't use solar power because you're so far from the sun. The sun's a little dot. So that we use these forever batteries. This is a tablet of plutonium-238. It generates so much heat, the surface glows red. So that's just glowing red hot. And if you could put these thermocouples around it, a Peltier cell, then just the heat from that fission reaction that's taking place inside that plutonium is enough to generate electricity. So it's only 7% efficient, so you need a lot of a radioactive element, which makes it really dangerous. But for satellites, great power source. 24,000 year half-life, it's not going to run out. And so that's nice. Doesn't need to be recharged. So these are nuclear batteries. The Soviets used them in remote weather stations in Siberia. And that's a problem because people have found them and stolen them. Some of them have come up missing. And so there's a few like really hot radioactive batteries like this running around internationally. Who knows where they are? And so that's probably the most likely source for a dirty bomb because it's highly radioactive and has a long half-life. So great. We've talked about all of these different electrical sources, conversions, and so on, and yet there's still some that we haven't tapped. Like we still haven't figured out a way to reliably capture lightning. The problem with lightning is it happens so fast. We don't have a way to capture it and store it because it's so fast it overwhelms the impedance of our capacitors and so on. So if we could find a way to capture the charge in lightning and then slowly leak that into a battery, it's that intermediate capture that we don't have. We don't have a net for that amount of electricity because it takes 1 millisecond. So that's 17 kilowatt hours per strike. It's a blast. I mean, it's in terms of megawatts, it would be 6,000 megawatts. And this is a picture of a plane being struck by lightning. And so this is a source of energy that we haven't even tried. I guess we're trying to tap into it. There's some people that are trying to direct lightning using the lasers. So you have a big panel that could charge up, so you direct a laser up there into the clouds and the ion trail follows back and then lightning strikes this panel repeatedly and they can try to store it, but it's a trick. So here's the references. So that's a take-home lesson, I guess, is it's hard to beat petroleum in terms of its portability, okay? But it is, our transportation is only 21% efficient. So if we could improve that, and maybe electricity will improve that, it would really be a golden solution if we could get to nuclear and use electricity then to transport ourselves. But we're so far from that. And in my opinion, I think we should not be focused on electrical vehicles yet. I think we need to be focused on the grid level nuclear, and then we will have the capacity to charge all our vehicles. Right now we don't have the capacity to charge them. Not just the charging stations, but the electrical capacity to charge them. So anyway, that's that.